Our speaker today, Anna Ciurlo, earned her PhD in astrophysics from the Sorbonne Paris Cité and pursued postdoctoral research at UCLA. She was an inaugural year Keck visiting scholar at Keck Observatory. Anna continues at UCLA in the Galactic Center Group as an assistant researcher and adjunct assistant professor. Her research focuses on stars and gas around the supermassive black hole in the center of our galaxy. Her work leverages high-resolution imaging and spectroscopy from large ground and space-based observatories like Keck and the JWST. Let me give you Anna Ciurlo.
So thank you for having me. So today, as Judy was saying, I want to take you all to a trip to the center of our own galaxy. But just before we start, I'd like you to just have a look at my personal academic map. So that's basically my journey toward astronomy. I am originally from Italy. That's my accent. That's where my accent is from. And then I did my PhD in France, but I also spent some months in Sweden, where I learned to love the research field of astrophysics. And then I came all the way to the other side of the world, basically to UCLA. And I got to spend several months in Hawaii, where the Keck Observatory is located, with this Keck Visiting Scholar program that allows young researchers to interact and with the researchers at the telescope, which was a great experience. And I used that experience to come back to UCLA and keep on working with the people at Keck, but also in Europe. So it's that's a typical example of a path of research in astronomy, and it's kind of all over the globe. And that's part of the fun and family as well. All right, but let's move on to the main topic of this talk. I want to take you to the center of our own galaxy, but exactly what is our galaxy and where is the center? What do I mean when I say the center of our galaxy? So probably many of you, if not most, have seen the Milky Way in the sky. It looks like kind of an arc that crosses the entire sky. And it looks like a hail of clouds, right? So you have this luminous band and then of gas clouds. And because of this white color, that's where the name comes from. It kind of looks like milk. That's the Milky Way. So what we see at night when we look at the Milky Way is the visible part of our own galaxy, the Milky Way. So because of the huge dimensions of our galaxy and all galaxies in general, we cannot really travel outside of it. That would take way too long. We don't have any spaceship that is able to do that. But we can get a pretty good idea of what our galaxy would look like if we could travel outside of it, if we look at other galaxies. So this that I'm showing you is not our own galaxy, but you can see some resemblance with the picture that I showed before of our own Milky Way. So this is the view we have when we look through the disk of our Milky Way. But if we could actually travel above it, what we would see is something like this. So our galaxy is what's called a Bart's spiral galaxy. So it's basically a disk, and we sit on this disk, and we see these spiral arms. So where are we exactly? Well, in these two views, the solar system is roughly 3/4 of the way toward the periphery of this disk. And so when we look at the Milky Way with our own eyes at night, we are looking through the disk, and that's why it appears like the top image. But the bottom image is what we would see if we could travel above it and look it from above. All right, as you can see, that has quite a complex structure. So let's look at it in more details. As I said before, it's very, very large. The diameter of our galaxy is around 100,000 light years. And as a reminder, 1 light year is the distance that light, which is the fastest thing we know in the universe, can travel in 1 whole year. So that's a very, very big distance. So imagine 100,000 times that very big distance. And our own galactic center is 26,000 light years away. So it's a little less, but if you think about how this works, when you look at the Milky Way, the light you're looking at started from the center of the galaxy 26,000 light years ago. So 26,000 years ago, that's roughly when we were still in caves doing paintings on the walls. So it was a very long time ago. So this is not a real picture. This is just a cartoon of the main structure of a galaxy. So we have the disk, then we have this kind of thicker part in the middle. That's what we call the bulge. And then all around you see this halo with these dots. So let's look at this as if we're looking at the map of a city. Because if you think about it, stars don't really live alone by themselves in the universe. They always live in groups of stars, which we call galaxies. So our own galaxy, the Milky Way, has a map, and so we can look at the different neighborhoods that exist in this galaxy. So we can start with these dots in the halo of the galaxy. These dots are actually all big ensembles of stars, what we call cluster, and in particular they're called globular clusters. And these host some of the oldest stars in the whole galaxy, so we can think about them as the historical neighborhoods of the galaxy, the ones that tell us about the past of our own galaxy. Then the main structure is the disk, the one we saw in the previous slide. And in the disk, we have the spiral arms. And on top of the spiral arms, you have the industrial areas. That's where stars are formed, and so they are born, but also where stars are destroyed, where they die. So they are very active and sometimes a little dangerous. But the regions in between the arms, this can be considered the residential neighborhoods. They are much quieter. Nothing much is going on. Maybe it's a little boring, but it's very safe. And that's where our solar system lives. So we're happy and lucky to be there. And then the topic of this talk is the city center of the city of star, the center of the whole galaxy. That's very crowded. It's very noisy. It's very exciting and a little dangerous, as we're going to see. So, but where exactly is it? So I told you before, this is what the Milky Way looks like when you look at it in the sky, but it's kind of hard to pinpoint exactly where the center is. So to find it yourself, you can get help from constellations. In particular, the center of the galaxy sits between the Scorpius and the Sagittarius constellation. I feel like the Sagittarius is the easiest one to pick out. It kind of looks like a crown, but many people refer to it as a teapot. And the tip of the teapot is the one that is pointing to the center of the galaxy that is sitting right there. So it's basically at the beginning of the dark cloud in that spot. All right, so how do we look at the center of the galaxy? Well, we have to decide many things. How exactly to look, what instruments to use, what wavelengths to use, and so forth. So let's see what that means. So this is just another picture of the center, well, of the Milky Way. And here is the center. So we know this is our galaxy. We know where the center is. So we look at it and what do we see? Not much, because most of the light is blocked by these clouds, right? So we need to do something different. This is a picture that is very detailed. It's taken using a good camera, but so it's much better than our own eyes, but still it's invisible. So it's taking this picture in the same light at which our eyes are sensible. But these are not the only colors that exist in the universe, right? So we can decide to look at it at this region, looking in the radio, in the infrared, in the X-rays. Many of you are familiar with lots of these colors or these lights or this wavelength, we call them as well. The electromagnetic spectrum, the spectrum of the light, goes between the gamma rays and the radio, and these are divided by the length of your wavelength. And so on the top, you have examples of things that are at that wavelength: gamma rays, the X-rays, ultraviolet, visible, infrared, and radio. And on the bottom, you have the size of the waves for each of these ranges. And you see we go from basically the nucleus of an atom to all the way to the distance between buildings. So it's a very huge range. And so when you select one of these range, you see different things. Our eyes are right in the middle where you see the rainbow, and they allow us to see many things, but not everything. For example, this is a beautiful nebula. We have a picture in the visible. It's very nice. We see this column of gas. But if we want to star these stars in this image, there is not much we can do because we cannot really see through this dust. So instead, we look at the slightly longer wavelength in the infrared. Infrared since it has a longer wavelength, it can pass through the dust grains that compose these clouds much better. And so we can see the light coming through. So this is exactly the same picture at the same scale, but taken in the infrared. And you can see there is still some gas around, some clouds, but we can really pierce through most of it, and we can see so many more stars. We can also do something else. We can look, for example, in the X-rays. In this case, you don't see a lot of things, but you see only the most energetic phenomena going on. So basically, the bottom line is you want to pick a wavelength range, a type of light, a range of light, a range of colors that allows you to see through your dust to look at the center of the galaxy. So here's the picture of the Milky Way. It's very pretty, but not very useful. We see a lot of stars, but most of the stars we see, they're not in the galactic center. The light from these stars is blocked by dust. So instead of in the visible, let's now look at this picture in the infrared. So same scale, same picture, but taken in the infrared. You see appearing many, many more stars. And in this picture, it's quite easy to identify the center of the galaxy is the brightest spot in this image. It sits right there. All right. So now we have been looking kind of at the global structure of the galaxy. We know where to look, but we want to start zooming in because this is kind of far away from the center of the galaxy. So let's start zooming in. So actually, maybe I should show you this previous image. It's much larger scale, and here I'm gonna start showing you the scale of the image on the bottom. It's 3 light years across. So if you remember, we started from the picture of the whole galaxy that was 100,000 light years. Then the distance between the solar system and the center of the galaxy, 26,000 light years. Now we are only 3 light years, so we are at a much smaller scale, and the center of the galaxy sits right there. So here in this image, I'm only showing you the brightest stars of all, but there are actually many more stars than this. And how many stars there is, I think it's very interesting if you think about a parallel with our own solar system. So in our old solar system, if we take the sun and we draw a circle that is 3 light years across, so 3 light years in diameter. So in the central 3 light years, let's say, we only have one star, the sun, because the closest star to us is Proxima Centauri. It's 3.5 light years away, more or less. So nearby us, within 3 light years, there is only one star, the sun. If you think about the same circle drawn at the center of the galaxy, so this is the galactic center, you draw a circle around it, then inside that circle, instead of just one, you have 10 million stars. So if we were to move the Earth to the center of the galaxy, you basically would see a permanent firework all over the sky at all times. So this is what it looks like when you show many of the stars, but again, these are a bit too many, so let's dim the lights a little bit, only show the brightest stars again. Still, there are many, many stars. If you want to look at this region in detail, you need a very, very, very high spatial resolution. How do you do that? Well, you need a very big telescope. The telescope that we have been using mostly is the Keck telescope. Actually, it's 2 twin telescopes on the top of the Mauna Kea mountain in Hawaii. So this is a picture of the Keck headquarters on the bottom, and on the top you see the mountain, and you can kind of see it up here. These are the telescopes. So these are bigger images. These are the 2 Keck telescopes, and you observe from the headquarters. Here is me and a colleague looking at the center of the galaxy several years ago, or you can look at it from here, or even from home, like during COVID, where we were all stuck at home during our observing. So how big are these mirrors? Well, the top left image is showing you that. You see there is a teeny tiny astronomer next to the mirror. That's kind of hard to see. So here is kind of a cartoon drawing of that. This is the size of the mirror of the Keck telescope. So it's a 10-meter diameter telescope. And just to give you an idea, this will be me standing next to it. I'm not very tall, but still you can tell it's a very big telescope. And the bigger the telescope, the higher the spatial resolution. So this is great, but we have one main drawback, is that we have to observe through the atmosphere. And the atmosphere has turbulence, and the turbulence introduces blurring. So even if you have a very, very big telescope, you cannot achieve the amazing resolution this will give you if you don't take into account what the atmosphere is doing to you. This is not a problem for small telescopes, but it is for big telescopes. So how do we do it? We cannot pierce a hole through the atmosphere, right? So instead, we want to correct for the effect of the atmosphere in real time, which seems crazy, but we are actually able to do that using what is called adaptive optics, and in our case, laser guide adaptive optics. So in this picture, you see the Milky Way on the left, the Keck telescopes on the right, and the 2 rays that you see, they are not fake. These are actually, it's a real picture that is not being retouched. So you use a laser guide star. So you kind of create a fake star that you point in the direction of your observation. And since you know that star very well, you can use that to measure in real time the effect of the atmosphere and correct for it in real time. So let's have a snippet on how that works. So you get the light from this fake star that comes from your laser. And you're going to see that the wavefront of this light is going to be all blurry, all curved, that kind of looks like a potato chip. But you actually look at the shape of this potato chip as it comes in, and then you feed it back to a mirror that is deformable so that can compensate exactly the shape of the wavefront. And so from potato chips, you actually obtain pancakes. You make your wavefront flat again. So this means that you're taking out the blurring. So this is an image of looking at a star with the turbulence of the atmosphere. You see it's kind of moving a lot. When you introduce this feedback look, then you have a much nicer point source. So before your star was all twinkly, now it's not anymore. So it's not very romantic because you're taking out the twinkle of the star, but it's very nice because you can actually see your star much better. And that's very important, especially in a crowded region such the one of the galactic center. We saw so many stars are there. So here are the lasers on the left. On the right is an image of the stars at the center of the galaxy, seen from a big telescope without adaptive optics. So let's see, we observe these stars, the center of the galaxy from Keck without any laser. What we see is that. So it's great, you see some stars, but actually we're very interested in looking in the middle of that white box, and you don't see much there. Everything is kind of blurry. So let's now switch adaptive optics on. What happens is that your image becomes much, much, much sharper. There are many more stars that you couldn't see before because they're all confused with each other that now appear. And what looked like nothing before in my little white square now looks like a lot of stars. And if you do this every single year, you see that these stars, they move. So you basically can measure how they move in the sky, and then we can also do something else. So this is basically called doing imaging. When you take pictures, right? You can take pictures in the infrared, in the visible, in the radio, and so forth, but these are still pictures. There is one more thing that we can do that is very powerful, that is called spectroscopy, which means that you not only take the light, but once you observe the light from a given target, you pass it through a prism, exactly like in the cover of a very famous band. And when you do that, basically the light from a star, for example, the sun, if you pass it through a prism, produces a rainbow, what is called a continuum. That's exactly the same process that produces rainbows in the sky when it rains. The little drops of water in the atmosphere, they act as this prism and they separate light. But if you have a cloud in front of a star, some of the continuum of the light coming from the star is absorbed by your cloud, and so you have what is holes in your continuum, what is called absorption. Or sometimes you can have the star or something else that is ionizing and heating up a cloud, and in that case, that produces emissions not like a rainbow, but only a specific colors that are called emission lines. So when we say a spectrum, that is an alternation of emission and absorption lines over a continuum, and is often expressed as intensity as a function of wavelength. And it's very important because different chemical elements emit at different colors or different wavelengths, and the way they move tell you about the way your source is moving through the Doppler effect, and we can talk more about it. But basically now we have an idea of how the star move on the plane of the sky by taking that picture at the center of the galaxy year after year. And we can also see how they move along the line of sight by taking their spectra. And the spectra tells us a lot about which type of stars we're observing and many, many more things. And sometimes you can actually combine these two techniques and obtain imaging spectroscopy. So if you have an image of a galaxy, for example, you can have just an image, or if you use a different technique, for every single pixel of that image, you can take that light, disperse it through a prism, and obtain a spectrum. So instead of just an image, you obtain a data cube. Think about it as a cake. So you have a cake where you have two spatial dimensions, right? And then one wavelength dimension. So for every single pixel, you have a spectrum as well. And that's very powerful because it allows you to study many different components of the images all at the same time. So we have talked a lot about many things we can use to study the center of the galaxy, right? So we want to observe in the infrared to allow light to go over and through the dust and come all the way to us. Then we want to use a very big telescope because it's extremely crowded. We need to be able to separate the different components in this very crowded environment. So you need a very big telescope, but a very big telescope, if you're on the ground, is not enough because the atmosphere blurs your image. So you need to do adaptive optics in order to obtain an image. And in addition to an image, you can also obtain a spectrum. So you can have imaging spectroscopy or imaging spectroscopy. So let's take all these things together. Through these techniques, we have been observing the center of the galaxy for now 30 years. And when you put this all together, what do you learn about what is in the center? All right, so what's in the center? Well, we can start from this. This is actually an image taken by the Hubble Space Telescope. And this is the one I showed you before. And now let's see. I want to really zoom in this image much more than we have done so far. So this is the region I'm interested in, and I'm gonna zoom in. So now this is an image that has been taken with the Keck telescopes using adaptive optics. And as I was telling you, we can do this year after year. So year after year, we keep on taking this image again and again and again and again. And so what I'm gonna do now is play an animation showing you what these different images look like year after year. You can look at the year yourself here on the bottom right. This is starting in 1995. Now let's start our animation. 95, now you have 2009, 2018, and then this where the animation ends. We have more data now, but we have not updated this animation. So all the dots that you see here, these are stars. And as you can see from the animation that keeps looping between 1997 and 2018, all the stars move, every single one, even the one at the corner of the image, they are moving. Every single thing is moving. But most of all, the things that are very close to the center are moving much faster. You can tell if you look at this bright star here, it's moving like this a little bit. This star here, if you look at it and you follow it, is making a full circle, a full ellipse around a point in the center. So this is great. If you actually study the motion of something around something else, you can learn about the masses involved. So basically, by looking at the orbit of the stars, in particular this star, this bright one that makes a full circle, we were able to calculate how much mass this guy here is orbiting around. And we figure out that the mass involved was 4 million times the mass of the sun. That's a huge mass. So imagine the sun, 4 million times that. And then you have to imagine squeezing that mass in a volume that is smaller than the distance between the sun and its closest planet. So this is an object that is very dense, so dense that it basically can only be a supermassive black hole. And this is exactly the way that people about 25 years ago were able to demonstrate that there is a supermassive black hole at the center of our galaxy, which made them be awarded with the Nobel Prize in Physics in 2020 to 3 people. Mostly I'm interested in the third one, Andrea Guess. That's the person I'm working with that started this dataset a long time ago, and that allows us to do this great discovery. But this is not the only thing you can do. There is so much more you can learn about this environment. It's interesting for many reasons. It's the center, the core of our own galaxy. So you want to learn about the core because the core, it's what regulates how a galaxy evolves and lives its life. And there is a supermassive black hole, and we are very interested in black holes for many different reasons. And then there are lots of stars, and studying how stars and gas behave nearby a supermassive black hole, it's interesting, and it's a laboratory that we can definitely not have on the Earth, and we don't have in the same way anywhere else, because every other galaxy that is not our own is going to be much further. So we know that the activity of the black hole itself, it's correlated with how a galaxy grows. Our own black hole right now is not very active. It's kind of quiet, whereas we see in other galaxies black holes of similar size on similar type of galaxies that are much more active. But we think this might be only a phase, because even though our own galaxy is not very active right now, it was most likely very active in the past. This is an image showing you Fermi bubbles. This is X-ray emission, and it's on extremely large scales. Again, we are here at the scale of basically the size of the galaxy itself. And these huge bubbles are probably coming in from a kind of accretion event or some energetic event that happened nearby the supermassive black hole itself. And we believe that because we see similar behaviors in other galaxies as well. So how do we actually make the black hole do this kind of fireworky behavior? Well, we believe that the easiest way of doing it is feeding the black hole. If you feed the black hole, then this can release a lot of energy in different ways through jets, through star formations, and so forth. So what you want to do is basically bring material onto the black hole to give it the fuel to produce this kind of event. So how do you do that? Well, let's go back to our picture. This is, again, a smaller scale, 3 light years. That's the size of the red arrow. And I showed you the stars, but there is not just stars. If you look in some of the different colors, you can trace the main structures of what is called the interstellar medium. So everything, all the medium that is not inside stars, is called interstellar medium. So it's dust, which we talked about already because it's the one that is blocking some of the light. Then you have gas. This gas is typically, molecular clouds composed of basic elements. And molecular clouds are interesting because that's where stars are formed, but it's also where stars release their energy and all the components where they die. So there is a feedback loop between the stars and the interstellar medium, but also between the interstellar medium and the black hole itself. Let's see why. So there are mainly 2 structures at this scale. The main one is the circumnuclear disk, this ring of gas. This is molecular gas, so that's the region where you could form stars. It's very massive, and it's the closest large reservoir of matter for the black hole. So this is the matter that most likely would be preferred if we want to produce an event such the one that produced the Fermi bubbles that I showed before. This ring is orbiting around the black hole, and maybe some of its material is infalling through the black hole. We do see this through this structure we call the mini spirals. A little bit of the gas is dripping in, but it's not enough for what we believe will produce something like the Fermi bubbles. But still, most of the, even though some of the gas is trickling down, most of the gas is kept away by strong winds that are produced by the stars that are in the center. We saw before there are many, many stars. Many of the stars are young and bright, and lots of bright young stars, they produce winds, and these winds basically keep this ring away. But as stars age, this wind would subside at some point, and when this wind stops, you can imagine that the material into this circumnuclear disk will be able to reach the black hole and maybe trigger this more active phase for the black hole itself. So it seems like there are 2 different regimes. There is this molecular cloud ring that is kept at a distance, and then there is the cavity inside this ring that is very, very energetic, very ionized. It has these strong winds. The stars also produce lots of radiation, so it's very, very energetic. But we found that there is actually some a small amount of molecular gas that is also inside this cavity, which is very surprising because we don't actually see it coming in together with these arms of the mini spiral, the orange structure, but it's there nonetheless. It's not a lot, but it's there, and it's quite confusing because it seems it's not coming together with the mini spiral, is not coming from the circumnuclear disk, and it's supposed to be destroyed very quickly by the very strong radiation coming from the stars. So one idea is that maybe it's produced around the stars themselves. We do see some gas around the stars. So our idea is that you have a star and then around it you have some gas. And this gas can produce this emission. But this emission is not enough to produce a very strong activity in the black hole. It's not enough food for the black hole. So we don't see any strong activity in the black hole connected with this amount of gas. So maybe we have to look into something else to find a different supply of food. As we saw, the largest reservoir is not going to be able to provide the food we would like to give the black hole right now because of the strong winds. So maybe for these very strong energetic events, we have to wait until this wind dies. But maybe we can have smaller scale accretion events or smaller feeding little snacks we can give the black hole and see how it reacts. And that's very interesting for us because it allows us to study how a black hole feeds and grows on small scales before we see this very energetic phenomena. So Let's go back to our zoomed in image. This is the same scale at which I showed you the previous animation with all the stars moving. And on the bottom left, you have a spectrum. So this is a real spectrum taken at the center of the galaxy. If you remember, when you have an absorption line, you're looking at the gas cloud in front of a star. That's actually the behavior we see for many young stars. They have a photosphere that acts as a cloud in front of the star. And so you can tell that emission is coming from the young stars in the region. But we also see emission lines, and we know the emission lines actually come from gas clouds that have been heated and re-emit. So if we look at the emission, we can study the interstellar medium, the gas, at the very small scale where we see all the stars orbiting inside this very ionized cavity very close to the supermassive black hole. So let's take again our picture of the imaging spectroscopy data. This is kind of the cartoon view of it, but on the right, I'm going to show you what the real data looks like. So you have, again, two spatial dimensions and one wavelength dimension. So we're basically looking at this along the wavelength axis, along the color axis. And as you can see, there is a lot of stuff. This is basically junk coming from the stars. And this is things that are along the line of sight. But what we're interested in looking at are these little cloudlets, these dots that appear outside of this line of sight emission. So what are these? Well, actually, these are gas clouds that we see appearing over and over when we look at our very long baseline data. And we basically looked at 15, 20 years of this data, and we keep on seeing them, and we can study how they move. How do we do that? Well, if you think about your data cube, your imaging spectroscopy cube as a cake, right? You typically slice your cake this way. So you can slice your cake on a chunk, on a range of colors or wavelengths, and then you produce an image. And so on the right, I'm showing you an image with three of these cloudlets that we have identified, and the red circles shows you the position of those clouds in 2006. Now, since we did this for several years, we can see how their position evolved with time, the same way we did for the stars previously. So let's cut our cake this way, and let's see an animation. So it starts in 2016 and goes all the way to 2020. And so you see the blobs are 1, 2, and 3, and you have them all moving away in the space of 15 years, right? This one is moving this way. This one started here and is moving away from the black hole, and so forth. But we have one more way we can cut our cake. Instead of cutting the reasonable way everyone does this way, you can decide to cut your cake this way. For example, if you want to put some jam in the middle of it. So if you cut your cake this way, you basically can extract the spectrum around each one of these objects and see how the spectrum evolves with time. So I picked one. This is the spectrum. This is the emission line. So this is the gas we see. And if we have cut our cake this way every single year that we have observations for, we can see how the spectrum evolves. And you see that your line is shifting away. This is caused by the Doppler shift, and the way this shift tells you if this object is moving away from you or toward you. So now we have two information, like we did for the stars, how the objects move in the plane of the sky and how the objects move along the line of sight, which allows you to create an orbit. So basically we found out that all these objects, all these little dots that we saw, not only they survive year after year nearby a black hole, but they also orbit around the black hole. So when the very first one of these objects were discovered, people thought, oh, this has gas emission, so it must be a gas cloud. That's what we saw, right? And if it's just a dust cloud, then if it comes close enough to the black hole, it must be destroyed. This is a simulation that shows you what will happen to a pure dust cloud if you pass it close enough to the supermassive black hole. The blue trays are the stars, and the red tray is this hypothetical cloud. So this was actually interesting because in 2012, when the very first of these clouds were discovered, it was predicted that the cloud would go through its closest encounter with the black hole only 2 years later. So there was a flurry of papers on what will happen to this gas cloud, and this simulation comes from all these studies and basically shows, okay, you have this star, in 2 years it's coming toward the black hole, what do you expect that will happen to it? And this is the expectation. So they expect it to getting more and more elongated and then eventually just being completely disrupted by this close encounter with the black hole, because a gas cloud is not very massive. while the star can happily orbit around the black hole at the same distance as this cloud, the cloud would not be able to do so because it has a much, much smaller mass, and so the gravity of the black hole has a much easier time completely spaghettified and destroyed quickly. So let's see if our prediction was met by our observations. So these are the very first observations of this cloud. That was the first one to be discovered. That was called G2. So this was its position in 2006, 2010. It's still a little far away from the black hole. Then 2012, that's when it was discovered the first time. Then we went back and saw the other images earlier. Here, 2014, starting to get very close to the black hole. And this is after its closer encounter, also in 2014. And as you can tell, this image doesn't map very well with the simulation I showed you before. This is not getting spaghettified. It's compact before going toward this closest approach with the black hole and also afterwards. So basically, we can tell that this cloud, G2, survived. So our initial hypothesis of it being only a gas cloud doesn't quite hold very well. So if this survived, and now we saw so many more objects that behave in a similar way, they basically show these emission properties of a gas cloud, but then basically behave like the other stars. They just orbit undisturbed around the black hole. Well, maybe that's because we don't see it, but there is a star hidden inside. So in this idea, you have, in this model, you have these puffed up stars that are disguised as dust clouds, dust and gas clouds, but actually are just stars in disguise. Now, the question is, stars usually don't show up in the rest of the galaxy looking this way. So why would they become so bloated up? What happened to it? And one possibility is maybe this is the merger of two stars. This is a picture, again, of the stars at the center of the galaxy, and by looking at the spectra of these stars, we can tell if they're old or young. The orange squares are old stars, and the blue circles are young, massive stars. And then we can look at the spectra of each one of these. And what we want to learn is, are they binaries or not? Why would we ask this question? Because we know that many, many stars, about 50% in our galaxy, are formed in pairs, in what we call binaries. But when we look in details at these stars very close to the supermassive black hole, we don't see any binary. So where are all the binaries? What happened to them? Well, maybe they all got smashed together by the black hole. How does that work? Well, you have the black hole here, and then you have these two stars that together, they orbit each other, and then together they orbit around the black hole. Now, the black hole has a very strong gravity because of this huge mass. So basically what it does is that it perturbs the binary and makes them getting closer to each other than they would otherwise. And if they come close enough to each other, they can start stripping material one from the other. And after a few cycles of that, you can actually have the two stars completely merged together. This is a very messy process that would shed a lot of gas and dust around these newly formed stars. And so you can imagine that this kind of process will produce exactly the type of object we see when we look at G2 and its other friends. So a bloated up, dusty star, where actually the star is hidden, but you see it through its dynamical properties, the way they orbit the black hole. So we now know about 6 of these that we call G objects, G2, 3, 4, 5, and 6, and we believe they all formed this way. There are many things in this environment. Many of them are interesting for different reasons. Here in this image, you see in purple the stars. The black hole, you don't see it, but I mark it with the presence. In orange, you see the arms of the mini spiral, that spiral structure I showed you before at larger scale. And then in red, you see the very dusty objects. So you can see G3, G2, and then what kind of pops out to your eye maybe is this very elongated structure here. This is called X7. And this guy here has similar properties to the G objects, but has a very strikingly different evolution through time. So I showed you before the animation of one of the objects, or multiple objects as they evolved in over 15 years. We can do the same for X7. This actually, it's over 20 years. It's just a cutout. The one in the middle here, this is X7. The black hole is up here. We start in 2002, and we run this animation for 20 years. And as you can see, this object starts kind of roundish, but then it completely goes away from that. Whereas the objects we saw before, the G objects stayed very compact and circled. Even the G2, when it went so close to the black hole, still was compact. This one here, this is really getting spaghettified. It's getting stretch and stretch and stretch and stretch. And I think that's actually what you expect to see when you see a pure gas cloud in the center of the galaxy. This one resembles much more to that simulation that I showed you a little earlier. How do you produce this? Well, it's very crowded in here, and some simulations show that the collision between red giants that have these very puffed atmospheres and the smaller, more compact object can produce this kind of filament-like features. Or maybe if we believe that stars that are formed in pair, they get smashed together by the black hole. During this smashing, maybe you also can release these filamentary structures. We are still kind of working the details about that. But what's interesting about all of these, the G objects and X7, is that they come very close to the black hole and they have all this gas around it. So they can provide little snacks for the black hole. And actually, we observed the black hole not long ago taking one such snack. So this is a picture at the center of the galaxy. Usually we cannot see the black hole. I mean, you can never see the black hole because nothing can escape the gravity of the black hole, not even light. So you cannot really shine a light at the black hole. The black hole does not emit a light itself. Well, when I say we see the black hole, we actually see the material around it, like in that image I showed you before of the black hole, that simulation. You can actually see the material that is not quite fallen inside the black hole, but is kind of orbiting around it and is ready to fall in. So when something gets added to that, what we call accretion flow, that's basically the ready-to-go meal for the black hole. When something is added to that, that produces light. And if that event of adding food to the ready-to-eat food platter of the black hole is big, you can have very energetic events, such as the Fermi bubbles. If this is not a very big meal, but it's very small, then you can have something that is much smaller, like the thing I'm going to show you. So usually you don't see that material, it doesn't emit a lot of light, but when there is something that is added to it, you can have a little enhancement of the light. So usually the black hole is right there, you don't even see it. But one night we saw it doing this. It got much, much brighter. So all the material, all this platter of ready-to-go meal for the black hole got something added on top of it. And this could have been something brought in by G2 when it passes very close to the supermassive black hole. Well, you cannot be completely sure, but that's what we believe, and it kind of fits nicely in a story that we can tell about the center of the galaxy and how things interact with each other. So we cannot really track it back to this huge event like the Fermi bubbles. We cannot track it back to accretion that will come from this very big ring around the black hole itself. But we can see this mechanism at play in real time, that we see that the black hole gets brighter when you feed it some material. So this is just a little snack, but in the future, maybe the black hole will have bigger meals and we will see bigger events taking place. And we were only able to do this using these very big telescopes. This is an image showing you the size of Keck, and also of the other very big telescope that is often used for this type of study, the Very Large Telescope, or VLT. And to scale, they are shown next to a basketball court. So they are quite big, but they are not quite big enough for what you want to do. We're in the process of building much bigger telescopes, but we can only do that on the ground. And to showcase that, these are the mirrors of the two biggest observatories we have in space, the Hubble Space Telescope and the very renowned James Webb Space Telescope. The JWST has been launched only a few years ago. Its mirror was so big that we have to fold it to fit it into a rocket and shoot it into space, but still, it's much, much smaller than the Keck and the VLT mirrors that are telescopes that have started operating 30 years ago. So, of course, it's much easier to build a larger telescope on the ground than on space. But the great advantage of space is that you don't have to observe through the atmosphere, so you do not need adaptive optics. But so, if we want to build a bigger telescope, we have to do it on the ground. And so this is the next telescope we would like to build, the 30-meter telescope. We would like to build on the top of the Mauna Kea mountain, or maybe in Hawaii, and also the extremely large telescope, or ELT, that is currently under construction in Chile, next to the where the VLT has been built. So the names are not very funny. We are not very creative with the names. Very large telescope, extremely large telescope, etc. But this is where we want to go. And for comparison, this will be me right next to these two gigantic telescope mirrors. And to give you a taste of how much more we can learn using this much bigger telescope, on the left you have an animation showing the stars orbiting the black hole seen from Keck. That's great. We were able to demonstrate with Keck the presence of a supermassive black hole. We can study the stars as they move. You saw how much more stars we see when we use Keck and adaptive optics. But if we use a much bigger telescope, also with adaptive optics as well, what we get is what we see on a simulation on the right. These two simulations are taken at the same scale, but you can tell that with a much bigger telescope, there are many, many more stars you can follow that are completely invisible and totally confused on the left. And this allows you to trace many, many more orbits, which tells you a lot about the properties of the black hole in the center of our galaxy. And again, this is just what we are doing at the center of our own galaxy, but there are millions or billions of other galaxies in the universe. So there is so much more we can learn by comparing what we see in our own galaxy to other galaxies across the cosmic time and across different stages of galaxy evolution. And with that, I want to conclude by showing you this beautiful animation of the stars at the center of our galaxy. The blue stars are young stars, the red stars are old stars, and the yellow trays show you the movement of these G objects, and probably also X7, I think, on the background of the rest of the galaxy. And you can tell that this is a very complex region. It's very crowded, it's very energetic. We would not like to have the Earth sitting right there because there is a gigantic black hole. There's all this radiation coming from young stars. Stars can smash into each other. So we definitely don't want to live there, but it's extremely interesting to study how the core of a galaxy work. Thank you very much for your attention.
Thank you very much, Anna. Very good presentation. Very, very nice. I really enjoyed it. What happened to the object that was sort of either coming from G2 or near G2 that was lighting up for a while near the center of the universe? How long was it lighting up, and was it sort of being formed into a new star, or what sort of happened to it after it lit up so strongly?
Do you mean in this animation or?
Yes. I believe you said something like it you thought it might have originated from G2 or near G2, and it was lighting up. How long was it lighting up for? And was it like the black hole kind of kneading it into a star, or was it just still kind of a gas cloud afterwards? What happened afterwards at the end?
So we saw G2 passing, kind of look not very affected by the black hole. We see it before the passage nearby the black hole. We see it afterwards. But it's always possible that some small amount of G2, big shell, dusty shell, puffy shell, could have been stripped away and could have fallen onto the black hole and produced this little snack. And this little snack would be shown in this animation. This bright spike in luminosity was only an hour or so.
Oh.
And so this basically shows the material falling nearby the black hole. So while the material kind of falls into this, I was talking about this ready-to-go meal, this disk of material that is not yet into the black hole, but is almost there. This is dense. And so when something gets added to it, the friction between this material and what is there already creates this spike in luminosity. So if that came from G2, it was stripped by G2. G2 continued with its own life because of the central star that kind of kept the rest, most of it together. The little piece was detached, was fed into this disk of material ready to be fed to the black hole, and it's never going to come out of it. It's just going to eventually fall into the black hole and then be gone forever.
Okay. So it's effectively part of the black hole. It's not being kneaded into a new star or anything like that.
No, to create a star, you actually start from a molecular cloud, so this massive but very diffuse medium, and then you have kind of dense, it's a little denser in some place, and if you have enough density, then the gravity starts putting together a star. You cannot do that nearby a black hole because the gravity around the black hole changes very quickly, so you actually strip the stars away before they can form.
Oh, I got you. It's like putting them into a blender. Got you.
Exactly.
Okay.
Okay, thank you, Susan. Uh-oh, I think I just put the hand down. I think it was Stella. Put your hand back up again. I think instead of unmuting you, I lowered your hand. So now I would have to find you. D.A. Nolan, Here's a question about what happened to SEI, the Search for Extraterrestrial Intelligence, which used multiple computers to look for signs of aliens, I guess.
Well, I'm not an expert on that at all. As I was saying, we don't want the Earth being in the center of the galaxy because it's so complex and energetic and dangerous. So for that reason, we don't expect to have many long-living planets in there. It could be that they form, but it's hard to imagine that they safely live undisturbed for long enough to form life. So for looking for the search for life is not focused at all in the center of the galaxy, even though you could have planets forming around stars like everywhere else in the galaxy, but and in the universe, but it's mostly focused nearby us. And there is one observatory that is in the process of being designed that is called the Observable World Observatory. But it's still kind of 20 years away or more, where the instruments are built especially to be able to detect life in many, many more planets than we can right now, but it's not quite ready yet. So I don't know if that refers exactly to that project, but that's what I know about the current status of searching for life in the universe.
Great, thank you. I have found all the texts where they went to. They've completely changed everything. This one is for Dan Darm, and it says, "Do other galaxies have black holes in their centers?"
Yes, very good question. We actually believe that most, if not all, galaxies also have this type of black holes. So we call them supermassive black holes because they are millions or billions even of times the mass of the sun. We know that stars that die in certain ways, they can also form black holes, but they are much, much smaller. These are called stellar mass black holes. So they are maybe the mass of the sun, half the mass of the sun, or 10 times the mass of the sun, and so forth. And but we know that the black holes that live at the center of galaxies are much, much bigger, millions or billions of times more. How do we form this? We believe maybe you take the stellar mass black holes, you put them together, and then they migrate toward the center of the galaxy, or we are not sure. The problem with that picture is that we don't find many of the intermediate mass black holes. So we have 10 times the mass of the time of the sun, or we have 1,000,000 or 1,000,000,000 times. We don't have 100 or 1,000 times the mass of the sun. So we don't know exactly why we have black holes at the center of our galaxies and why they are so big.
Thank you. This one's from Ron Schulp. He says, "Are you surprised that there's no such a clear line of sight from the solar system straight to the Earth in the Milky Way? It seems that there should be some of the stars in that field of view. They're at random distances between here and the Sagittarius star."
Yes, so indeed, but the problem is that I showed you, right? The Milky Way is a plane, right? It's a disk, and we sit inside the disk, and the disk is full of gas. If you think about the picture seen from above, you have all these spiral arms. So no matter where your line of sight crosses, it's very likely to cross toward the arms of the spiral, right? So you are gonna look through this dust no matter what you do. You cannot avoid it because we sit inside that dusty gas disk. If we were just in between galaxies, then you would not have much of this problem. You would still have some of that problem, but not that much. So we do see some light coming through. It's not like we don't see any light coming from the center of the galaxy, but the very, very center is very obscured because the closer you are to the center, the more stuff you have along the line of sight. I hope that kind of answered the question.
When the James Webb Telescope went up, there was a lot of fuss about it. It was just amazing pictures and shocked the whole world. But around after that, I heard talk begun of a follow-up to James Webb Telescope. They only have a name for it. They're going to call it the Carl Sagan Telescope. It's supposed to be another 40-year project, and the mirror is projected right now to be twice as large as the James Webb Telescope. And they're going to do this, evidently the saying, put it at a Lagrange point and be infrared and all that. Do you know anything more about that?
It's hard to say because these telescopes take a very long time, much longer than the original projected time, often because they need to be designed. So in order to be then approved, they have to be budget, but they also have to kind of reach the milestone in design that they require. So they want to build a telescope that is basically slightly bigger than the Keck telescope, but in space. Then they have to be able to say, okay, how do you assemble this? How do you shoot into space? How you deploy it, and so on. So this is why it's always hard to know exactly if a project is going to go toward the end, because they need to be able to basically develop the technology that allows you to do that. And often some of it is there, but not everything. So it's what is a plan, it doesn't mean that it's necessarily approved. So this is what I think it is just a very early phase of this. So it's the design phase when you try to figure out what kind of technology designs and advancement you need to actually build it. So that's why it's 40 years away or more, maybe.
Okay, thanks.
The interstellar medium near the core should be highly ionized, which suggests that electromagnetic forces should be significant in controlling cloud motion. Have you and your colleagues played with that idea?
No, so it depends. Everyone is kind of expert in a different field. There are people that are expert in magnetic fields, but it's kind of a joke in the field that, oh, well, this is all true unless you consider the magnetic field. It's always, especially when you try to build simulations of things, it's hard to fold the magnetic field into it. But there are people that look into that, and that's helpful mostly in the sense of interpreting your data and creating simulations that are realistic on how all this interact with each other. And when you do an hydrodynamical simulation without the magnetic field, it's hard to completely believe it. So it's not quite my field. So I mostly do observations and then try to interpret them. And the other thing is that we have type of observation that can trace the direction of the magnetic field with an instrument that calls polarimeter. So there are studies of that as well, but they were mostly done with the Sophia Observatory that has been recently decommissioned, so it's going to be hard to follow it. So to answer your question, yes, we kind of looked at that. It's sometimes hard on the theory and the observational side, but it's something that we do consider.
Have your studies of black holes, there's a mysterious thing called dark matter. Mm-hmm. Have your studies of black holes thrown any light on the mystery of this dark matter? Can you tell us?
Yes and no. So when we look at the black hole and the stars around it, we can look at the motion of the stars, and basically that tells us about properties of the black hole, but we have to take into account all the mass that is doing something to the stars, because some of these effects are extremely small. So when you consider what the black hole is doing, you expect the orbit of your star to do something. Basically, when you think about a star, its orbit is going to precess, so start moving this way. Instead of going back exactly to the same spot, it's shifting a little bit, and that precession is due to the black hole. But it can also be due to what is called extended mass. So all the mass that are not stars that is enclosed in this orbit that is also affecting this. So that mass could be just stars that are not detected, because our observatories, they have sensitivity limit, so you cannot detect very faint stars, and so it could be something you just don't see because it's too dim. But there could be a lot of it, so it could have a gravitational effect, or maybe it's dark matter. It's hard to disentangle those two. So that's the closest we get to dark matter. Usually dark matter studies are done across galaxies on very large scales, because again, gravitation is a very small effect, so it's hard to see it on this small scale. They also look at dark matter in clusters, because as the star moves away from the center, as the further you are from the center, you're supposed to be less affected by the gravity of the cluster. So if those stars move too quickly, then can escape that cluster. And so you can do that in the center of the galaxy as well, see which stars can escape, but it's very hard to say if that is due to dark matter or something else. Whereas in more isolated clusters, you can say, oh, these stars, actually, they are very fast, but they don't escape. Maybe that's because of dark matter. So that's more adapted to study dark matter than the center of the galaxy.
How big is the black hole in the center of the Milky Way? How many times the mass of the sun?
4 million times, a little over 4 million. And it's not one of the biggest. There is the first image of a black hole that came from the Event Horizon Telescope that was out a few years ago. That's from a galaxy nearby, and that's billions of times the mass of the sun. I don't remember exactly how many billions, but billions, not millions of times the mass of the sun.
I'm sorry, it says, why does it have a spike in luminosity before going into the black hole?
So why we see that spike in luminosity before something falls into the black hole? I think that's the question. And the answer is because you already have some material there. So you basically have the black hole. And then around the black hole is what is called the accretion disk or the accretion flow. So material that is kind of trapped around the black hole and it's not fallen into the black hole yet, but is eventually going to fall into the black hole. And all this material is moving very fast, and it's basically a plasma. It's very dense. So when something else gets added to this material, this accretion flow, the friction between this and this material makes this spike in luminosity. It's kind of like when meteors enter the Earth atmosphere and they catch fire, and you see shooting stars. That's also kind of getting brighter, and it's not exactly the same, but the idea is that it's friction that is producing this spike in luminosity.
Okay. Dan Durham asks, what elements are in the gas clouds?
Oh, a lot of different elements. So mostly hydrogen, that's the most abundant element in the universe. But there is also some simple molecules. There is CO. There's been traces of lots of more complex molecules as well, as ice especially. And you have some heavier elements like heavier than iron usually come from supernovae explosions, and these explosions basically what happens is that these stars themselves, they change the elements, right? They start with hydrogen and they make it heavier and heavier up to iron, and higher than iron is basically only through supernovae explosions. But when these stars lose mass or explode, they basically shoot back all their material into space, and that gets trapped into gas clouds again. So if you have heavier elements, they come from supernovae. So how heavy the elements are inside a gas cloud depends on history. Was it nearby an explosion like a supernovae explosion or not? So you have heavier elements or not. But in general, mostly they are just made of hydrogen. Oh, and Stan posted his question, so maybe I can read it. What is the orbit time of the fastest star going around our galactic black hole? So we don't know which one is the fastest because maybe we have not seen it, but the fastest that we know, it's I think around 6 years. But the one that I showed you that did the full circle, the one we used to demonstrate there was a black hole, has an orbit period of 16 years. And we use that one because it's brighter, so it's easier to follow it than the other stars that are fainter. But we hope that with TMT and the ELT, we can see shorter period stars, we can follow them more quickly, combine the different, because now we only use one star to basically estimate the properties of the black hole, the mass and the distance to it. But with more stars, we're going to be able to do it, and hopefully also faster if the orbits are shorter.
And I think you've really already answered this, but he also says, isn't dark matter just a theory?
Dark matter?
Yeah.
Well, we have not found exactly what particle could be dark matter. So basically, dark matter is not a very mysterious thing. It's just something, okay, we see a gravitational effect, but we don't see any light coming from it. Whereas all the matter we know usually emits light. So maybe there is this type of matter that has gravity, has mass, so produces gravity, but doesn't emit in any of the colors we see, not in infrared, not in the X-rays, none of them. So that's why we call it dark matter. And so it's very simple. We see the gravitational effect of a matter we cannot see. We don't know which particles are made of it. And there are a lot of particle physics experiments that are trying to pin down which type of particle create dark matter. But I think it's pretty solid theory. It could be that it's wrong. We were wrong before. But I think it's not so mysterious. We might find out that there is nothing that quite fits it, or maybe it's just too hard to detect it. But the thing that is very mysterious and we know nothing about is dark energy. Dark energy is different, even though the name is very similar to dark matter, but it's different because dark energy is the thing that basically is pushing the universe to expand the way it's expanding. It comes from, it's much harder to imagine than dark matter. Dark matter is just invisible matter, basically. Dark energy is basically a force of which we don't know anything about. And it comes from equations as early as the equations of general relativity from Einstein, and seems to be coming back, but we don't know exactly what is producing it, why, and exactly how it works.
Can you briefly describe the difference between a galaxy with what is termed with an active center and one that is considered inactive? And where on the scale does the activity you have reviewed here for the Milky Way fall?
So if I understand this exactly, this is about difference between different level of activity in a galaxy. That's right. That's the question, I think. So usually what we see around us is all different quantity of activity. So usually we call active galactic nuclei galaxies that have extremely bright centers that emit a lot of light, and there is a lot of radiation, there is a lot of stars being formed. And we call safer galaxies, or just quiescent galaxies that don't have lots of light coming from the very center. They are not actively forming lots and lots of stars. And our galaxy is basically a pretty quiescent galaxy right now, but we believe it was more active in the past, because so we see traces of this higher activity, like the Fermi bubbles, but other things as well at smaller scale. And so in other galaxies, the same, we only have a snapshot, right, at what stage each galaxy is. So we use basically their brightness and which type of light they emit to figure out which type of galaxy they are, if they're active galactic nuclei, or for short AGNs, or quiescent galaxies. And so depending on which type of light they produce, we do that through spectroscopy. We can tell which type of object they are. So just looking at the shape of their spectrum, the shape of their light as a function of the color of that light tells you which type of object that is.
Kathy asks, this project uses data over many years, and she wants to know how you get so much time on the Keck telescope.
Well, the Keck observatories, they observe all year long, and we basically get maybe 14 nights, or maybe less, maybe 14 half nights. So yeah, maybe 10 nights a year. And you have to write a proposal to get that time. The time for Keck is reserved to the so University of California, all of them, Caltech, there is a bit for NASA, so everyone is this chunk of time, but you still have to apply for time. So you write down a proposal and you get allocated with time. And what we did recently is put down proposals that are for observing not each year, but we want to do this project over several years, so we want to have a time scheduled over 6 years, and so we got the time that way. But also the telescope recognized that the study of the center of the galaxy is very rich, and it has been during the years kind of pushing the telescope and the technology a lot. So it's very often used as a test case for testing new technologies and development at the telescope. So it's a kind of a partnership between the group doing the observations and the telescope and the people developing the instruments and pushing the technology forward.
Ray Holston says, thank you. And he wants to know, how do you calculate the mass of a black hole?
You use the stars. So when you look at the way the stars move, so that star that did the full circle, looking at its orbit, you can calculate the mass, because the shape of the orbit depends on the mass of the objects involved, and the black hole is much more massive, so the mass of the star doesn't really matter, but the mass of the black hole is what basically help you trace the orbit. So that's the way you do it.
Is the future of the universe for all matter to be consumed in black holes, and perhaps future Big Bang in the distant future?
That's a good question. We don't know. There are different models that have different predictions. Some predict that the universe will just keep expanding more and more, so things will be just getting further and further from each other. And if they're further from each other, then they cannot interact. So basically, that's the future of a very cold and dark universe, where stars just die and then nothing happens to it. It just keeps hanging around without anything around it. Or it could be that the universe stops expanding and actually starts contracting again. And in that case, that's kind of a hotter universe where everything gets smashed together. Then in that sense, yes, you will have more material going into black holes, but maybe not everything. And then you will go back to what they call, instead of a big bang, it's kind of the inverse of the big bang, contracting everything into a big crunch. So these are kind of the two main theories, but there are many more where they say maybe you can have galaxies, and then maybe you can have kind of big bangs within big bangs. So there are a lot of different theories, but it's very hard to test them. The only thing we can test for is whether the universe will keep on expanding or contracting, and dark energy is right in the middle of this type of debate. And it seems like the parameters we have calculated so far tell us that we are exactly in the. So it's either that it's going to be forever expanding and then, or the opposite, that it's going to start contracting. And this might be because that's just how life is, or it could be because there is more to the theory that we have not discovered yet, or maybe something in between.
He said, did supermassive black holes or galaxies form first?
That's the next question, I guess. We don't know. The only thing that we know in a straightforward way how to form black holes is stars. So we do need stars to form black holes. Stars typically form in groups, and these groups are within groups, and these groups are called galaxies. So exactly where the line ends, it's hard. Maybe very primordial stars were kind of all together, but there were always primordial galaxies. But probably the first stars formed first. So I would bet that probably the black hole formed first, but chicken and egg question. Since there are empty particles for each particle, could dark energy result from black holes made of antimatter be repulsing rather than attracting other matter? Well, the problem with gravity is that it has a distance of influence. So if you are too far from a black hole can eat anything. It's like a huge monster can shark down everything. But you have to imagine it as a huge monster with very short arms. So only if you're close enough is going to reach you and destroy it. So I don't think that the black holes, antimatter black holes repulsing would explain the push, because there would not be enough of it and would not be far-reaching enough to explain how this acts as huge. But
all right, Anna's been here a really long time, and I want to thank you for spending this much time with us, Anna, and giving us such a wonderful presentation. I've had a couple of things in the chat saying how great it was. Thank you very much, and have the rest of your day.
Thank you.